Today. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this morning and for another week. Just pray that you'd guide our thoughts today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So, today is an exciting day. Today we begin our discussion of Galois theory. So, Galois theory, which of course is named in honor of, well, Galois. Galois was a French mathematician. Just to set the stage for you, I think in the late 18th century, and probably also through the work of Euler, but especially Lagrange, back in, well, let's see, 500 years ago or so, Cardano, Tartaglia, these other folks, they found, Ferrari, found or communicated at least solutions to the cubic and quartic equations, right? And, well, of course, the quadratic equation was known in various notations for a long, long time. I won't say more because otherwise I will rain down upon me a unending stream of comments of historical corrections in my YouTube video. If this so happens, if I have the misfortune of someone actually noticing I said something here. So anyway, I am not going to wager an opinion on the starting point of the quadratic, but it's old. So it seemed like there's this trick you can do. You take the next to leading term, and you can kind of like eliminate it or something. It's called a depressed polynomial. So we do this trick in the completing the square, right? We eliminate the linear term by lumping it into the quadratic. Something similar is done in the cubic solution. You take the quadratic term and somehow suck it into the cubic term, make a cube, something like this. And so there was, and then that somehow ends up being successful in the quartic. You've probably never seen the formula. My wife worked it out in high school. It's like a page. So it seems like if we just keep going, maybe we can find there's sort of the quintic formula, right? An arbitrary formula for finding the roots of a fifth order polynomial with rational coefficients in terms of sums and quotients and products of roots and elementary arithmetic operations on the coefficients of the polynomial, a quadratic formula, if you will, for the quintic. And so Lagrange was no slouch, and he tried to generalize those calculations that had been done elegantly by those Italians earlier, and tried and came up with whole new mathematical apparatus and methods involving permutations, essentially, and other things, and just was unsuccessful. And so by the end of the 18th century, mathematicians began to believe, maybe we can't do it. And so then we saw the first sort of no-go proofs in the start of the 19th century. Ruffini, although there seems to be some disagreement that he actually had a proof, but he claimed to prove that there was that there did not exist a general quintic formula for arbitrary fifth order polynomials. But then I think generally it's agreed on that Abel, depending where you're from, gave a good proof that you could not find a analog for the quadratic formula for fifth order polynomials in about, I think, 1826. All right, but again, he didn't say. It was just I think he just I haven't looked at the original paper or anything, but I think basically it's here's an example, and this specific one, or at least this specific class, you cannot do it for this reason, for X reason. I don't know what the reason was. I'm not sure how his arguments were. I'm not a math historian in that sense, but then in 1830, well, somewhere in there, Galois, who was at that time, I guess a teenager, probably younger than you guys, or about your age, came up with what we now call Galois theory, where he not only showed that Abel was right and Ruffini was right. In fact, there do exist polynomials which do not have a quintic formula. But he also showed a method by which you can say which ones do by calculating what we now call the Galois group. So long story short, if we look at a polynomial and its Galois group is solvable, basically there exists a formula for the roots. If it's not solvable, then no. I think that's pretty much it. I guess we're done. No. So, but we'd like to understand what this mysterious Galois group is and how these ideas sort of unfold. You've already seen hints of it in what we've done so far, but that's the big picture. So, definition. An isomorphism of K is an automorphism. Right. So the collection of all these things we call what? Aut K. That's point number one. Point number two. An automorphism fixes A, all right, in K if sigma of A is equal to A. All right. And so the next definition surprised me slightly, but it's his definition, so I'm going to stick with it. And then he says that if if sigma, an automorphism in K, fixes each A in F, which is a subfield. Well, I guess it doesn't have to be a subfield. No, a subset, rather. Just a subset. So if it fixes each A in some subset of K, then sigma fixes F. Sigma fixes F. And that's an if and only if, too. I mean, I would sometimes, we talk about invariant subspaces, right? For like a linear transformation, T of W is a subset of W. But I don't insist that each point in W is a fixed point of the map, right? So this is stronger than the notion of invariant subspace because we're actually assuming point-wise fixing here. So, okay, anyway. So he makes some sort of obvious comments here. First of all, any field has at least one automorphism. What is it? The identity map, sometimes called the trivial automorphism. So if we have, I need a letter. If we have a field L, right, and that's an extension field of K, so suppose this is the prime subfield, right? Prime subfield of L. Now he says that L is generated by 1. Could you guys explain what that means? We know that prime subfield is either what? What are our choices for prime subfield? It's either got characteristic 0 or it's got characteristic of prime, right? If it's characteristic 0, the prime subfield is the rationals. If it's characteristic finite prime P, its characteristic subfield is F sub P, right? So what does it mean generated by 1? I'll get you started. I can get either Zn, right? Or I can get Z. Let's stick with characteristic 0 for the sake of me not going nuts. So let's assume that the characteristic of L. Oh, I'm sorry. Did I say L? I know why you guys are confused. I meant to put K there. All right, there we go. Assume the characteristic of K is, all right, there. So if the characteristic of L is 1, first of all, I can build the integer. Good grief. So this goes back to a comment I was telling Emily earlier, which is I stayed up entirely too late making up new homework problems for Calculus 3 because they're like, "We really want some practice." I was like, "Fine, I'll make them." But then other things happened, and it was very late until I got that done. So here I am. I'm trying. All right, getting back to the story. Characteristic 0, add 1 repeatedly, we generate the integers, right? But then we can take that, and then we build the field of fractions over that. And then, voila, that's the, that has to be contained in the field L because it's a field. So, you know, fractions of integers have to be in the field, whatever, I mean, the isomorphic copy of the integers inside L at least, right? So in so doing, we generate the prime subfield as we described before. All right, so just just a comment about what he means by that, all right, in case you guys forgot. All right, so any automorphism, so we have, you notice that if sigma of 1 is equal to 1, right, for any automorphism, right? So what's that say? And it's, k is generated by 1. I mean, so right. So sigma, an element of aught L in my current notation, right, automatically fixes what? Right. The prime subfield K. We don't continue using K as a dedicated notation for prime subfield in this section. Don't get carried away, okay? And that, of course, is because sigma of AB is sigma of A times sigma of B, and you know, sigma of A over B is sigma of A over sigma of B, provided B is non-zero and so forth. All right, definition. Sorry, I'm going too slow on this part. I'll move along. Let K over F be an extension of fields. All right. Then we let aught K over F be the collection of automorphisms of K which fix F. All right, in other words, what? Sigma is an element of aught K over F means what? Two things, right? First of all, sigma is an automorphism of aught K, right? And also we get sigma of X is equal to X for all what? For all X in F, right? So a silly example is if we look at the, you know, if we're in characteristic 0, the automorphisms of K over Q is what? Yes. And yes. Yeah, the point is that the fixing of the prime subfield comes for free, so yes. Every automorphism of a characteristic 0 field is automatically a rational fixing automorphism. Every automorphism of a field of characteristic P is automatically a finite field with P elements fixing automorphism. I need a better name for that. I miss Z mod P. I guess I have to go with F mod P. What's the standard name? I don't know. All right, moving along, moving along. Now, this proposition gave me unnecessary, what's the word, jitters, angst, suffering, confusion last year. Aut K is a group. Okay, that we've already proved last semester under composition. All right, so we have that from last semester, right? I mean, the composition of isomorphisms, ring isomorphisms is a ring isomorphism. Anyway, the fact that the automorphisms of a field form a group, I think this we have from last semester. What's next is new, though. Well, maybe this is even a homework problem for you. I don't know. I mean, this could very well be a homework problem from last semester if it wasn't. Aut K over F is a subgroup of that group, right? So the fact that it's a subgroup means we can use subgroup tests, of course, right? So let's see here. Suppose that sigma and tau are in aut, the F fixing automorphisms of K, right? And we should do what? Let's let X be an element of F, right? What happens when we look at sigma tau of X? What do we get? I mean, by definition of composition, it's sigma of tau of X, which is sigma of X, which is X. So consequently, sigma tau is an F fixing automorphism, right? And here's the place where I got stuck. How do you show sigma inverse is an F fixing? Sigma inverse of X equals 2. And the thing that it's a stupid thing, but for whatever reason, last year, for the life of me, it did not dawn on me that I should just go, oh yeah, well that's sigma of X. Duh. Right, because it's an F-fixing automorphism. And so that's X again, which shows you that. And if you search your heart, you'll remember that there was a homework last semester which explored this exact calculational feature of the group theory. It may not have been exactly this, but the calculational nuances here were present in at least one of your homework last semester for sure. All right. So the F-fixing automorphisms of K form a subgroup, and a little bit more than that. This proposition 2 is quite beautiful. Let K over F be a field extension, and alpha, an element of K, algebraic over F. So we've got an algebraic element alpha in K over F. Then, the end of the sentence, then for any sigma in aut K over F, in the F fixing automorphisms of K, sigma alpha, right? Which, by the way, is our notation for sigma of alpha. This is commonplace in this chapter. We don't necessarily write parentheses for a function evaluation, right? Beware of that. Sigma alpha is a root of the minimal polynomial Where was I? For alpha over f. To put it into words, the f-fixing automorphisms of K permute the roots of irreducible polynomials. Equivalently, any polynomial with coefficients in f having alpha as a root also has sigma alpha as a root. All right? So here's the proof of that. So let's suppose that we have, alpha to the, alpha to the n, a sub n minus 1, alpha to the n minus 1 plus dot, 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 plus alpha, let's say a sub 2, just a sub 1, a sub 1 alpha plus a naught equals to 0. And that's supposed to be the minimal polynomial where? So here, this is based on what? X to the n, a n minus 1, x to the n minus 1, a1x plus a naught, an element of what polynomials over what field? This is the minimal polynomial evaluated at the element. Where is this minimal polynomial? Where are the coefficients from? F, right? All right. So in other words, the coefficients here, just to be annoyingly pedantic about it, the coefficient, to be clear actually, the coefficients are elements of the base field F. So then what do? We take an f-fixing automorphism, let sigma be an element of K over F, and act on the above. What do we get? We get sigma, right, of all that stuff. Now it's sigma of 0. All right, so I'll put down just a couple steps since this is kind of important. I don't usually put all these steps down, but so one of the things we can, of course, this first thing just becomes sigma alpha to the n, right? And then we've got like sigma of an minus 1, sigma of alpha to the n. I should have chose coefficients that don't look like alpha, huh? Sorry about that. Tell you what, I'll make it better by putting tildes on my coefficients. That'll make it so much better, right? Whee! Whee! All right, moving along. So what did I do? I used the additivity and the multiplicativity of the automorphism to pull apart products and to pull apart the sum. And the power rule for homomorphisms, remember, we pull out the powers. That's all going on here. So many rights and privileges that we have learned from last semester at play here, Seems like I have doomed myself to bicolored equations. All right, so, but of course, I'll fix it. This is really just what? This is really just an minus 1, right? This, of course, is just a1, right? This, why are these just those? These are, the coefficients are in F, right? Sigma fixes F. And so what do we have? We have, basically gamma to the n, plus an gamma to the n minus 1, plus dot, 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 plus a1 gamma, plus a naught tilde equal to 0, where gamma is equal to sigma of alpha, right? Which is to say that gamma is a root. of the same minimal polynomial, right? It's the same. This up here, of course, was m alpha f of x. And this calculation shows that m alpha f of gamma is equal to 0, right? Okay, so there you go. I think I could have spent half the time. You guys still would have understood. So I'm just making it last longer because I enjoy the feeling of understanding what I'm doing. Sorry. All right. This is the time in class where I have to remind myself our class does not end at 8:50. I should relax. We have another 15 minutes. Yes. Okay. So next he gives 3 examples which really sort of set the stage for the discussion in the rest of the section here. So his example 1 is he takes k equal to q adjoin the square root of 2, right? And he says, okay, well, if tau is an element of, the automorphisms of q adjoin square root of 2, fixing q, well, that's just, as we were just discussing, that's really just saying it's an automorphism of q adjoin root 2, right? And so what does it take to define, I mean, what does q adjoin root 2 look like? Remember, this is just a plus b root 2, a and b rational. I'm about to write reals there. Not a good sign. All right. All right, so let's think about it this way. Every automorphism, I don't think you're going to get information from the fact that the automorphism fixes the rationals, right? So everything that makes the automorphism sort of interesting is about the sort of irrational part, if you will, of the field. So really the question is, what do we do with root 2? Where can we send root 2? Those are the possibilities that will tell us what kind of automorphisms we can have here. So if we think about it, we have to have tau of root 2, right? It has to be equal to something of the form a plus b root 2, right? Yeah, and so further analysis will show you it has to be sent to plus or minus root 2, because to do otherwise we'll end up giving you contradictions in terms of yeah. Exactly, it has to be something the squares give 2. So precisely plus or minus root 2. So there really just are 2. Either we have tau equal to the identity, or we have tau, tau of a plus b root 2 equal to a minus b root 2. Remember, it fixes the a part. That's just the rational piece. So tau of a equaling a that's not for grabs. That follows from the fact that tau sends 1 to 1, and 1 fixes the prime subfield. So of course you might recognize this. This is kind of that. It's not complex conjugation, but it's kind of sort of like complex conjugation. It's at the heart of all the similarities between rationalization of, square roots from the denominators and putting things in Cartesian form for complex, right? These are all kind of the same algebraic beast. Oh, so in short, what are the what is this then? Ought. Q join square root of 2 is actually equal to, and so this would be what? Basically the 1 tau, yeah? So let's not say that this is tau, let's just say the identity, right? So it's either this or that, if I'm going to use tau as being that fixed map there. No, he changed the notation. I'm sorry. He used tau for the variable, and he called this thing sigma. I am trying to stick with his notation in as much as I can, because he does keep using this notation later. Sorry about that. So, if you understand, so tau is his variable isomorphism, and he's labeling his choice of this by sigma. Okay. I'm not saying anything especially deep. All right. Example 2. If we look at k equal to q adjoin the cube root of 2, all right, then basically tau is going to be defined by its action. He says tau is completely determined by its action on cube root of 2 because tau of a plus b cube root of 2 plus c times the cube root of 2 squared is equal to what? It's equal to a plus b. So where is this formula coming from? You know, oh, and I should get in the habit of not writing all these unnecessary parentheses. So why the ABC just come out, right? Because those are rational coefficients. Tau is an automorphism which fixes Q, pulls out ABC, and you see, so to define the tau, to define an automorphism of Q adjoining the cube root of 2, it suffices to say where is the cube root of 2 being sent.
So if tau is an automorphism of Q adjoining A, then it's induced by an isomorphism on the multiplicative group generated by A.
Yeah. I think that's fair. So, on the other hand, we know that tau, now here we go, tau adjoining cube root of 2, he says must be a root, right, of what? What's the minimal polynomial of the cube root of 2? This we've talked about in chapter 13. X cubed minus 2, right? Now I can picture those in the complex plane, right? Here's your happy-go-lucky cube root of 2, and the other guys, they're over here, right? Here's your cube root of 2, zeta 3. Here's your cube root of 2, zeta 3 squared, right? Those are your other solutions to the minimal polynomial x cubed minus 2. Where are those? Are those in K? They're not. This is an automorphism of K we're looking at. So we cannot send the cube root of 2 to either of those complex roots. We have only one choice. We have to send the cube root of 2 to the cube root of 2. So this proves that there is, it's lonely, but tau is just the identity. The Q fixing automorphisms of Q adjoining cube root of 2 just contains one thing, the identity automorphism. Make sense? I hope so. So these three examples we're looking at, again, they really just frame everything that happens afterwards. It's important for me not to skip them. Oh, I can't count. These two examples we're looking at. All right, so he says in general, K is generated over F by some collection of elements, then any automorphism, of F, any automorphism of K which fixes element of F is completely determined by what it does to the generators, vindicating Sam's question in a slightly more general context, right? Yeah.
I think my question is actually incorrect because I was thinking that we could just have any permutation of the basis, but that's wrong.
There's going to be, I think there's going to be a context in which your intuition syncs up, but we need further definitions. Yeah. If K over F is finite, then K is finitely generated over F by algebraic elements. So by the proposition, the number of automorphisms of K fixing F is finite. That is, the K F fixing automorphisms K is a finite group. So in particular, the automorphisms of a finite extension can be considered as permutations of the root of a finite number of equations, right? This gets back to the prehistory of this subject, really getting back to Lagrange, and the fact that you sometimes hear about group theory just being about permutations up till, about the turn of the, up until about 1900, more or less. Well, maybe 1890-ish. It depends on where you're in school, I suppose, but for a long time, group theory was just about permutations. And that's because group theory was about Galois theory, which was about permuting the roots of polynomials. All right, so he points out at this point that we have associated, let's think about this. We have associated to each field extension, K over F, right? A subgroup. Sorry. A group what? K over F, right? The group of automorphisms of K which fix F. And in fact, we can reverse this. So this is proposition 3, is that, here, well, I'll just write it down. Let H be a subgroup of the automorphisms of K, right? Subgroup. Then the collection F of elements of K fixed by all elements of H is a subfield of K. In fact, I will, I'll give you the proof in a second, but let me just tell you, once we get through that, then that gives us the right to make a definition. This subfield in the proposition, it's called F, right? In the definition which follows, it's called oh, he doesn't give it a name. Well, the subfield F is the fixed field of H. All right. So the proof of proposition 3, it's not that long, really. So what we'd like to prove that this collection of F elements fixed by elements of A. So pick A and B in F, right? And let H be an element of H, right? So if you look at, to prove this is a subfield, F is a subfield of K, what do we need? Well, sure. How about this, H of AB? H is an automorphism. So this is H of A, H of B, right? But H fixes A, H fixes B. So this is A, this is B. So H of AB is H of AB. Likewise, H of A plus B is what? H of A plus H of B, because we're talking about an automorphism. But it fixes, I mean, it's almost... So like if A and B are fixed by elements of H, then so are A times B and A plus B, and well, 1 goes to 1. That's already so. So let's see here. And likewise, the inverse. We also have H of A inverse, right? Is equal to H of A inverse, which is equal to A inverse, because H of A is A, so. All right, anyway, it is a subfield called the fixed field of H. And I will save, well, I guess I should just, I want to, let's see here. So anyway, what we'll be looking at, among other things, is these extensions, finding automorphisms, and studying the interplay between these fixed subfields and these subgroups of this nature, and what the interplay is between these fixed subfields and these subfield fixing, these particular special kinds of automorphisms, and that. Anyway, not a story I can finish today, but this is a long section. It's going to take me a few days to get through, and I don't want to rush it because this section, understanding this section, is the most important part of the chapter. Yeah. So, thanks, guys. Sorry I didn't get further.